Longer battery life is important for mobile phones and other portable devices. Short of a breakthrough in new battery technology, the easiest way to make improvements in operating life is to accurately characterize the dynamic battery current drain of the device and reduce the drain where possible. Current drain in a device such as a mobile phone has a complex nature related to the network environment, user behavior, and device complexity. However, even if a repeatable suite of user events is compiled for testing, the underlying operating system and subcircuits may contribute a significant amount of random behavior in the battery current drain over time. So, before making any design changes, you should log the long-term current consumption over the duration of the test suite as a baseline for comparison. This captures the random nature of the current drain activity as well as the more predictable events. The result is a more accurate measure of the total average current drain. In the following example, we will use measurements of mobile phone standby current to illustrate this point. The difference in average battery current drain before and after a design change is the net impact of that change. The objective is to try to correlate the effect of a design change on the current drain activities related to that change. One approach is to manually scroll through the data log and examine the amplitude and duration of specific current bursts related to the design change. Not only is this process time-consuming, but may result in incorrect conclusions unless many events are accurately recorded and averaged. And each time you make a design change, this tedious process must be repeated. Fortunately, there is a better way to look at the data using probability distribution functions, or PDFs, to display current drain values logged over a given time period. A PDF shows current drain values on the horizontal axis versus probability of occurrence on the vertical axis. Histograms are a well-known version of a PDF. But histograms are not very useful for analyzing battery current in mobile devices because of the extremely wide range of current values demanded by these devices. A cumulative distribution function is the summation of the probability of a PDF. The total area under the curve equals 100%. When plotted on a log-log scale, it also provides some compression of the wide range of current drain values. A more visually intuitive form of this data is the complementary cumulative distribution function, or CCDF. This function shows the cumulative probability of the current drain for any specific value over the whole range of current used by the device. It is commonly used in the mobile phone industry for analyzing battery current drain characteristics. This graphic shows the long-term current drain values logged on a mobile phone during standby operation. Design changes that affect the current drain level of standby operations will appear as shifts in the horizontal direction of the curve. Changes that affect the duration or frequency of those operations will appear as vertical shifts in the curves. Agilent Technologies has this CCDF calculation and display capability in a solution designed specifically to solve this difficult measurement task. The N6781A source measure unit is tuned for battery drain data logging and analysis. When combined with an Agilent N6705B mainframe and 14585A software, it is a superior solution for measuring and analyzing battery current drain in devices such as mobile phones. This graphic shows the CCDF display of standby current in a mobile phone during continuous receive mode. Then a CCDF of standby current during discontinuous receive mode was created and displayed so the differences can be easily compared. Agilent 14585A battery drain analysis software gives you quick insight into the change of average current and total power consumed. You can also see how much of the reduction in power consumption is caused by the changes in probability at various current levels. Here, at 128 milliamps on the horizontal axis, a vertical change from 3% probability to 0.16% probability resulted in an 18% power savings in standby current. And here you can see that a horizontal change from 14.2 milliamps to 3.3 milliamps resulted in a 55% power savings in standby current. There is also a 27% power savings from reduced baseband activity. Note that these data and curves include standby current and all random activities that occurred during the data logging period. The total overall power savings was 85%. CCDFs provide you with quick visualization of the impact of design changes on battery current consumption. Characterizing and optimizing battery runtime for your device has never been easier. For more information, visit the Agilent website at www.agilent.com/find/N6781 or contact any one of Agilent's authorized distributors.